Well, hello everyone, and welcome back. This is our fourth lecture, and in it, we're going to be discussing about recursion, trees, and dot dot dot. Well, you might have guessed by now. I always put that dot 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 in in there is because we have to figure out how far we get, and depending on time, I might jump to the next topic, which is heaps and priority queues. But if recursion and trees end up taking a lot of the time, then I'll stop at trees. Okay, so let's jump right into it. Recursion, a fancy name, but a simple concept. Simple after you understand it. The process in which a function calls itself directly or indirectly is called recursion. And the function that does it is called a recursive function. Now, the example that I'm going to show you is a direct recursion. The definition talks about indirect, but mostly the way I've used it is directly. And then using a recursive algorithm, certain problems can be solved quite easily. Now, so simply put it, a function that calls itself again and then again and again, well, you're thinking, well, isn't that going to be infinite? No, you are going to have some sort of an exit condition that the last copy of the function that gets called, how do you come back to the very first one? So this is what the syntax might look like. You have a function called recurse, okay? The recurse call recurse. It's going to call itself. So the main function is going to call recurse, and then that function ends up calling itself. So the way it looks like is when this one is called, the control of the program goes here, right? And then when you're in it, that method calls itself. It's as simple as that. This is a direct recursion. One of the famous example that exists up until this day is the factorial example. What is factorial? 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, right? So in it, we're gonna call with the number 4, okay? And how does that work? When you say result is factorial n, and in the factorial method, we say if n is greater than 1, okay, then you return n times factorial n minus 1. Otherwise, you return 1. Now, the return 1 is actually the exit condition um, of this recursion. Now, what's going to happen? Just follow this logic. So 4 is still greater than 1. So what's going to happen is n is 4. I'm going to do 4 times factorial n minus 1. Then I end up calling factorial 3. Okay, so there's another copy right here. So I'm in 3. Is 3 greater than 1? Yes. So then I call 3 times factorial n minus 1, which is 2. Okay, we go again. Is 2 greater than 1? Then you call 2 times 2 minus 1, which is 1. Aha, so now you're finally at this 1. Is 1 greater than 1? No, return 1. So 1 comes here, all right? So you end up doing 2 times 1, which is 2. You go here, right? So 3 times 2, right? Because you get the result 2 here. So 3 times 2 is 6, and that 6 goes here, right? 6 times 4 is 24, that goes here. So that is the final result. That's how you go about dealing with factorial. I have an example here. And that example is that of factorial. So I take it, in that example I showed you 4, right? 4 factorial. What if I ask the user for a number? So I say 5. But you get the point though. This is the same factorial method that's used, except what I'm doing here is I'm asking the user for an input. And that input, I'm saying it's got to be non-negative, right? And then I call the factorial method. And finally I end up getting the result that I want. Now, it all sounds great, fine, and dandy, but let's talk about the pros and cons. Obviously, we're going to talk about the pros first. It makes the code, yeah, it makes the code very short and clean. I mean, a factorial, instead of doing if, then else, or right, repeating a bunch of lines of code over and over and over again, you get away with less lines of code, and it's cleaner. And recursion is required in problems concerning data structures and advanced algorithms such as graph and tree traversal. We haven't talked about trees yet, but something to keep in mind that recursion really helps in going through the nodes of a tree. Red, black tree, binary tree, what else? So we're convinced of recursion, but there are some disadvantages too, right? It takes a lot of stack space compared to an iterative program. So it's going to consume up memory because it's going to have all these copies of the program in there. It uses more processor speed, and it can be difficult to debug compared to a iterative program, right? Because you gotta mentally you gotta have this picture or draw it out or however you're gonna debug it. It is going to take time, but I think the advantages outweigh the disadvantages. And up until this day, I use recursion. Okay, let's go into our next topic, which is trees. And then after this is where I had the dot 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 in the main in the lecture 4 slide. What I'm about to cover is a fairly complicated topic. Now at this point it seems straightforward, understandable to me, but when I was studying this I had quite a bit of trouble. Now tree. Now what you're gonna have to do is use your imagination as much as you can for as long as you can and try to work off of a pictorial memory. I do have pictures in here, but I want you to use your imagination. So what is a tree? We all know what a tree is, right? So, but in programming, C sharp and C++ and Java, a tree is a data structure. It's a hierarchical data structure that's used to represent data in a way that's easy to navigate and search, right? Or you look at a tree outside, you're like, well, really? But, when it comes to the O of N, the runtime, it's pretty fast to search for something in a tree. The tree is a collection of nodes that are connected by edges and has hierarchical relationship between the nodes. So there is a node, there is a leaf, there is a root. We'll study these terminology, but just have a picture of a tree, okay? A visual tree, you know, in your mind, it'll make things easy. Now, the topmost node of the tree is a root, and the node below it are called the child node. Each node can have multiple child node, and each child node can have its own children, right? Forming a recursive structure. So this is where recursion is going to come into play. When you're going to traverse the tree, you're going to use recursion. So this is what it looks like. You have a root node, a mother, that gives birth to all these children. Right? No. They can be siblings. Um, so A is a root. It has two nodes, right? B and C. B and C, they have further children. B's child is D, D's child is H, H's child is K. The bottom level, the last level of the tree, the nodes in there, the nodes that do not have any more children, are called leaf nodes. Okay, keep this in mind. Root, the very first one, the top, the mother, the main, Eve. Okay. Leaf nodes, no more children after that. Siblings. Okay. Two nodes at the same level. Okay. Uh, Now, I hope it's understandable why E and G are not siblings, because E and G have different parents. G and F are siblings, E and D are siblings, but E and F and G, them three, they're not siblings at all. Okay? And this is the height of the tree. Level 0, like as it is, similar to what the array, how it works, the uh, starts at level 0 all the way to level 4, right? What did I cover? Root, edge. There's also this concept of edge, okay? Siblings, child, parents, subtree, head of the tree, leaf nodes. Okay, so we're going to use this terminology throughout, and hopefully it's clear and it's not confusing. Now, one thing I should point out is any questions, issues, please, let's set up office hours, talk to me so I can explain this, because this is fairly complicated at this point. Very useful, yet complicated. Now you have the root node, right? And then why are these called subtrees? Because they are trees in and of itself, right? So you've got these three children. These three children will have more children, and so on and so forth. So this is a recursive data structure. And this is what the node might look like. Okay, so you have, remember we studied about linked list? So you have a node, in it there's data, and then that node has children, right? First child all the way to the nth child. And how are these connected? These are connected via pointers. Now, you can already guess what kind of implementation. Is it a stack? Is it a queue? Is it a linked list? Single linked list, doubly linked list, circular linked list? What kind of data structure is used in this? What I'm not going to do over here, I'm going to ask you this as a homework question, right? I'll come to it at the end. But I'm not going to show you an example in code. Well, the code is there of traversals, but I'm not going to cover in detail an example of I'm creating this tree, okay? This is something I want you to do as a homework exercise. And, you can copy paste it from web somewhere, but I highly discourage you to go that route. Think of a picture in your head, think of a data structure, and then start implementing it. Because if you copy paste, you're not going to get it. And once you have it written down, the traversals, searching through going through the tree is going to be a piece of cake. Now, the one tree that we're going to, the different types of trees, right, in C++ and in Java. There is a red-black trees, there is a binary search tree, or binary tree. The one we're going to focus on in this lecture is a binary tree, okay? Now, what is a binary tree? In binary tree, each node can have maximum of 2 children. Okay, some common types of binary trees: binary tree, complete binary trees, balanced binary tree, and degenerate or pathological binary trees. Just think of binary trees as a parent that can have 2 children at most. From a coding perspective, there's nothing preventing you from a parent having 3 children. Okay, but this is what a binary tree looks like. What shall I cover next? Okay, I'm hoping by now you understand trees, nodes, level of the tree, parent, child, and sibling. Right? You with me so far? And what is a binary tree? Now, if I were to ask you this in an exam, what's a binary tree? Hope you'll be able to answer that it is a tree which has a maximum of 2 children to it. Okay, a parent cannot have more than 2 children. And the operations of a tree. Obviously, there is creating of a tree, insertion of items in the tree, searching. Search specific data in a tree to check whether it's present or not. right? So you go through and search for something in the tree. Traversal is how do you go about scanning. There are three types. Actually, there's fourth. I'll cover the fourth one in the next slide. There is pre-order traversal, breadth-first traversal, post-order. Pre-order means perform traveling a tree in a pre-order manner. That doesn't really give it away. I'll cover this in more detail. And the same thing for post-order. Perform traveling a tree in a post-order manner. Nope, that doesn't explain it either. I'll give you some steps. Another approach is to traverse the tree so that we visit all the positions at depth D before we go to D plus 1, right? So you'll go look at all the siblings and then go to the next level. So you'll do it each level at a time. In order. Okay, now this is going to be more, you're going to understand this more. Now imagine a tree, right? You've got children, and I say we're going to traverse this in an in order manner. Well, how would you go about it? In order, you go to the left tree, okay? Then you call in order again. So you keep going left, 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 left until you hit the bottom. And then you come back up, you visit the node, and then you go to the right. So everything on the left gets printed, everything on the right gets printed, then you come up to the very top. I do have a picture of these traversals, but right now, use your imagination, right? Hopefully it's going wild, but you're getting the hang of it. You don't need to memorize all of this, how the in order is working. You need to just understand it. Pre-order, right? One is in order, pre-order, post-order. Breadth first, you got the hang of it, but there's in order as well. In order, pre-order, and post-order is what we're going to cover. Pre-order. Pre means before. You visit the root, then you go to the left, then you go to the right. Right? You display root at data, then you go left. Right? And once you've done all the way left, then you go right. Now, as you might have guessed, and as I was hinting at earlier, all of this is going to happen via recursion. Post order, you visit all the nodes on the left, all the one on the right, and then the root. So pre was you start with the root, left then right. Post, left, right, node. In order, left, root, then right. In order is kind of intuitive, right? First you go to the left, then you come back up to the root, then you go right. Pre, you go start with the root, then left, and then you go right. I think pre-order might be intuitive for you guys, right? Not the in order. And post is just left first, right after, and then root at the very end. Post after. So root is an afterthought. So think of it this way: pre, post, in, all has to do with the root. Post, roots at the end. Pre, roots first. In order, left root, then right. Now let's look at this example. So you've got a tree, right? 1, 2, and 3 are siblings. 4, 5, 6, 7 are the leaf nodes, and 1 is the root. In order, what do? You go all the way left. 1, 2, 4. Print 4. You come up 2, right? And then you go right 5, and then you go up, and then you start going left, which is 6. You go up 3, and then right. Pre-order. What are we gonna do? You start off at the root 1, then you go all the way left 1, 2, 4. So you get 1, 2, 4, and then you go to the right. You get 5 right here. Then you go up, and then you go right, and then left, and then right. Post order, all the way to the left, right, and then your parent, and then all the way to the left again, and then you go 7, you go 3, and you go 1. Right? Confusing enough for you? I'm sure it is. Um, One thing I could do is let's look at an example here. I've got a couple of examples, one in Java, one in C++. Okay, of these pre-order traversal, post-order, and then in order. Hopefully these will kind of make sense to you. And one thing to keep in mind, this time I've got an example of Java and C++, right? In the past I've only had it um, for C++. So I've got a node, okay? Let's look at this. I've got a node, and it is data, and then a struct node left and right. The node data. This set data has got data. Left is equal to right is equal to null. That's the definition of the node right here. We're gonna come. You're gonna see. See, when I created a structure root, so I have the root is 1, and the two children of the number 1 are 12 and 9. Okay. 12 has a child 5, right? And then 12 has a child 6. So one parent, one root, which is 1, two children, 12 and 9, and then two leaf nodes, 5 and 6. Now, the way I'm going to go about this is I've got post order and I've got in order. Post order, now, one thing I have to do is when you're doing recursion, you need a terminal or an ending condition so that your recursion ends. In this case, if the node's null, then I return. That means I've reached a point where I'm looking at the child of a leaf. Okay? Otherwise, if that's not the case, then I say post order traversal node at left. I go left first, and then I go right, and then I output node at data. Okay? And you know what's going to happen, right? This is going to go into recursion. So you're going to have copies of it. You're going to call it again and again. Now, in order, you go to the left, then you print node at data, and then you go to the right, right? And then you can kind of see how the well, there's in order pre and oh yeah, there is all three of them are in there: pre-order, post-order, and in order. And let's look at a Java one. It's very similar, right? Even the syntax is similar. No, it says Java, but it's still C++. Anyway, sorry about that, guys. I should have typed in Java. But anyways, let's go ahead with this one. Yeah, because the compiler is Java and I've got C++ code over there. Not to use request. This computer's slow. Let me go to Google. Sorry, guys. I should I always have this typed up, but this time, 9 C++ compiler. Maybe I should have it bookmarked. I'm missing a return 0 and let's give it a try. So there you have it. That's the in order, pre-order, and post-order traversal. Play around with the example, and then see what you come back with. And I think you're not gonna totally get this when I'm lecturing you guys on it or trying to give you examples. You have to try it out for yourself. Up until a point where it becomes intuitive to you.